We had quantified translation motion using position, displacement, velocity and acceleration. Similarly, for rotational motion, we have to develop new set of terms to quantify rotation motion. They are angular position, angular displacement, angular velocity and angular acceleration. Let's now understand them in detail. The first term we learned was position. Similarly, for rotation, we will use angles or angular position. As we had defined displacement as change in position, we will define angular displacement as change in angular position. This follows the regular sign convention as for angles. That is, movement in anti-clockwise is considered positive angular displacement and movement in clockwise is considered negative. For a body moving continuously in a circle, its angular position changes with time. The rate of change of angular position is called angular velocity. We obtain angular velocity by differentiating angular position with time or by finding the slope of angular position versus time graph at any point. Finally, we have angular acceleration. It denotes the rate of change of angular velocity. We can obtain it by differentiating angular velocity by time. Like their counterparts for translation motion, these quantities too follow the three equations of motion, which is, as we know, valid for constant angular acceleration. Note here that omega naught is angular velocity at time 0. These quantities can be related to their counterparts for translation motion. For instance, we know angular displacement or angle in general in radian is related to arc length or distance by the relation distance is equal to radius into angular displacement. If we differentiate this, we will get speed is equal to radius into angular velocity for a body moving in a circle with constant radius. Similarly, if we differentiate this term, we will get magnitude of tangential acceleration equal to radius into angular acceleration. We should be careful at this point before digesting this particular information. Let's understand the difference between tangential acceleration and radial acceleration. Suppose there is a body moving with velocity in this direction. If it has an acceleration in the direction aligned with its velocity, this will change speed of the body but will not cause any change in its direction. This type of acceleration, which just causes change in speed, is called tangential or angular acceleration. This is because it acts tangential to the path of the body, which is also the direction of velocity. But if the acceleration is directed perpendicular to the direction of velocity, it will not cause any change in its speed, but only cause change in its direction, which is precisely what happens when a body moves in a circle with uniform speed. If we consider such a body, though its speed is not changing, its velocity changes with time. This change in velocity is just caused by change in direction of velocity. Hence, it is accelerating, and the direction of its acceleration is towards the center of the circle. This kind of acceleration, which acts perpendicular to the velocity of the body, which just causes change in its direction, is called radial acceleration or centripetal acceleration. Its value is given by expression radial acceleration is equal to v square by r, where v is the magnitude of velocity or speed at that particular instance and r is the radius of curvature at that particular instance. A body can express both radial and tangential acceleration. Consider this body with this velocity and experiencing an acceleration like this. This acceleration can be resolved into two components. One as radial acceleration, causing it to move in a circle. We can also find the instantaneous radius of the circle using the relation radial acceleration is equal to v square by r, and tangential acceleration, which causes change in speed and thus is also its angular velocity. which is governed by the three equations of motion. Remember that this is applicable even if the body is not moving in a circle of fixed radius or with uniform speed. These values would denote the speed and its radius of curvature at that particular instant, with component of acceleration perpendicular to the velocity at that instant.